All right, cool. Yeah. So yeah, my name is Mikkel, and gonna tell you about TinyDA, which is a software package for multi-level delayed acceptance, Markov-chain Monte Carlo. As Linus said, I work for the University of Exeter, but also for a spin-out from the University of Exeter called digiLab, which is sponsoring the online platform. We're a startup, and we work in uncertainty quantification for the industry. So I lead the consultancy branch of the company. Some of our customers are the UKEA, the Atomic Energy Authority in the UK, and Jacobs with his engineering company, and Southwest Water, and a few others. We also built a software platform called TwinLab, which is uncertainty quantification for beginners, or for non-experts. And then we have an education platform too, which we call digiLab Academy. But in any case, today I'll tell you about first a little bit about the algorithm, multi-level delayed acceptance, and then I'm gonna show you the software package TinyDA, and then some examples of real-world problems where we've used TinyDA and MLDA to solve it. So this is something I put up in every talk I give, more or less, because it's important to remember, and it's true. Monte Carlo is a bad method. It's extremely costly, and you probably shouldn't be using it. But sometimes you have to, and that's why we do all this, work on these methods, is because there are just some things where you need it. So first, just for those of you who haven't seen this before, but you probably have, this is the Metropolis-Hastings algorithm. That's a way to draw Monte Carlo samples from a Bayesian posterior distribution. So that means that that you have a prior distribution, and then you condition it on some data, and then you can get samples from that posterior conditioned distribution. And it's a sequential algorithm, so it's quite expensive for some technical reasons that I don't want to go too much into here. And therefore, a lot of effort is being used on making this more efficient. And one of those approaches is delayed acceptance, MCMC, where you have two models. You have a cheap and an expensive model. The cheap model is some variation of your model that's maybe has reduced physics, or a coarser grid, or something like that. But it's still relatively close to the true model that you're really interested in sampling from. So what you do here is you take a single Metropolis-Hastings step. That's the first line here. You take a single Metropolis-Hastings step using the coarse model, and then you promote that state to a proposal for the fine model. And this is written here in the most kind of general form. So for the Metropolis, for the delayed acceptance ratio, this QC is the proposal on the fine level. And you can write this in different ways depending on what that coarse proposal looks like. This is the most general form down here, but if you have a state independent coarse model, then it simplifies to this expression here in lemma 1. So pi star is just the posterior distribution induced by the coarse model, and pi t, pi target, is the target distribution. And you can do that because when the coarse model is state independent, then it's in detailed balance with the coarse distribution. And so what the MLDA algorithm does is first to take multiple steps on the coarse level. So when I showed delayed acceptance, it took one step. But for this MLDA, for 2 levels, you'll take multiple steps on the course level. And that means that you kind of decorrelate the proposals to the fine level, so you get some statistically more independent samples on the fine level. And you can do that. We've proven that the composition of 2 steps is also in detailed balance with the course distribution. And the full multi-level acceptance just consists of doing that recursively. So you can have any number of modeling levels, so from 0 to big L. And every time you want to take a step on a level, you run a small chain on the level below. And on the lowest level, you just run Metropolis Hastings. And if you design this right, you can really get a lot of bang for your buck with these types of algorithms. And they're also relatively simple to implement. So yeah, that's multi-level delayed acceptance. There's also a little trick that we've developed to extend this. So this is an idea that since you're evaluating the same kind of parameters for the course and the fine level, you can build a model of the bias of the course. So that's what this shows. This equation just shows how we extend the data generating model in the Bayesian inverse problem with the bias term. And this f fine minus f course is something we can evaluate every time we promote a proposal from the course. And if we do that, we can bring the course distribution that's illustrated here in the red isolines, we can bring that closer to the true target. And this was a method that already existed, but for when we developed this algorithm MLDA, we extended it into a multi-level setting where you can do this for any number of levels. And you do that by just computing these error models recursively. Okay, so on to TinyDA and how the software package works. So you can do either standard Metropolis Hastings, delayed acceptance, or multi-level delayed acceptance. Those are just those are chosen automatically under the hood, depending on how you set the hyperparameters. It comes with a bunch of different proposals built in. So yeah, some of the more modern ones are these like precondition Crank-Nicholson, PCN, and operator-weighted PCN. Also comes with Muller and an approximate Muller, which I call kernel Muller here, which basically computes a gradient approximation from historical samples. You can also easily extend these proposals by writing your own. There's a base class that you can extend. It already implements the error models that I talked about earlier. You just have to set a flag and use an appropriate likelihood function, and then it will do this correction automatically. And so on the right, there's just kind of a flow chart of how the information flows around inside of TinyDA. So it's written in pure Python. It's open source. You can contribute if you like. It's written fully imperatively, unlike most of other kind of probabilistic programming languages. They're usually written in a declarative way, but I prefer just kind of like the look of imperative, so that's the thing. And it has very minimal dependencies. So I've tried to really kind of to limit it to only the essentials. But it has Umbrage support, so that's really easy. If you have an Umbrage model, you can just plug it in and sample from the posterior. And yeah, as it's pure Python, it's pretty easy to read, so you should be able to extend it for your own applications. So here's a minimal example You can set up a prior. That's just an object from SciPy. So SciPy stats ships with a bunch of different distributions, and you can pick any of those as your prior. The likelihood, so SciPy sadly doesn't implement any likelihood, so you have to, well, TinyDA comes with a Gaussian, but you can subclass and build your own. Model is just something that takes in a vector of parameters and output the forward model. And then you put that into a posterior object, so prior, likelihood, and model. Then you can initialize a proposal, and there's a few to choose from, as I showed on the previous slide, and then you just run sample. And then you can convert it to an ARVIDS object. So this is like an inference data object that allows you to plot all sorts of diagnostics using ARVIDS. If you want to use umbrage, you can just initialize your umbrage HTTP model and then feed it into this TinyDA umbrage model. This pre is if you need to do a transformation of the parameters before they're fed to the umbrage model. So for example, I let the MCMC sample in like log space of this Gaussian process, but the force model takes like in, yeah, I need to exponentiate it so it's, you know, positive. So you can do that within the umbrage model class. And then you just put that into the posterior like you did before, prior, likelihood, model. You can set up the proposal and so on and sample from that. So that's pretty straightforward. Okay, so I'm just going to show you a few applications of TinyDA and umbrage. So this is a tritium desorption problem from nuclear fusion, and it's joint work with Stephen Dixon, who works for the UK AEA. The forward model is a finite element model built on the Moose framework, and the way we did this was to hook up Moose with an umbrage server. Then we drew some QMC samples from the prior distribution of input parameters, and we built a GP emulator, and then we ran TinyDA with a GP emulator as a causes model. So yeah, a Gaussian process emulator, I should say. And we used the full finite element model as a fine model. And what you see here to the right, the bottom right, is samples from the posterior against the actual experimental data that they had. So yeah, I think what's interesting here is that there's this area here which is relatively unconstrained. So I guess if you'd want to run, you know, another experiment on this rig, you'd want to sample there to kind of constrain this experiment more. And this is just a write-up about how this functional GP stuff works. Like, it's because we wanted to simulate the entire curve and not just the value at the data points. And so we did like this proper orthogonal decomposition of the output curve, and then you can emulate the modal strengths of this POD decomposition with a GP and project that back into the POD space for the emulator. Here's another example of an application with this bit similar approach. We hooked up this exahype, which is some of Anna's work. Parabolic solver with map of this tsunami model, and then we set up a three-level MLDA where we used the GP emulator as a causes model, the model it was trained on as the intermediate, and then the finest model of this tsunami model on the top. And we could also use these prior samples that we used to train the GP emulator to get a first estimate of the proposal covariance. And yeah, the bottom plot shows how this scales on the cloud computing platform where the fine model was running. So this is some experiments I've been running recently. I'm interested in kind of like higher level geometrical priors. So for example, this is a convolution problem. So you have like a mesh distribution here on the left, and this could be a gravity and like a gravity measurement. So you have some heavy objects underground, and then you measure them on the surface. So you measure their effect on a gravitometer. And so, yeah, this is the true underground density, and this is then what you measure on the surface. And we want to recover this true density. And you could do this using, like a Gaussian process prior, but that's smooth. And if you know that, your objects aren't smooth, then you probably shouldn't be using a smooth prior. So what we did here was to use a Poisson process prior. So you can describe the distribution of these points in space, and then you can sample from that. And what you see in the bottom is the mean, and it's mislabeled the right one. It should be variance. So this is the variance of the posterior distribution. So what you can see here is that this, rightmost blob is almost invisible here because of all the noise in the signal, but we can actually recover it using these Poisson point process priors. And yeah, you can see this ghostly variance around it. So this type of prior comes with TinyDA. So if you're interested in this kind of like high-level object modeling and finding maybe the boundaries of an object, then you can use that. And this is like some of the most recent work I've done. This is joint work with Dave Higdon and Colin Fox. So this is an old problem that Dave has been working on for many years, and it's a very difficult inverse problem because of this prior. So this is a Markov random field prior, and the interesting thing here is that if two neighboring cells are differing enough, then well, how should I put this? It's kind of like neighboring cells have to have the same value unless they're far enough away. Then they're allowed to vary free. So this can give these kind of like very strong differences, like these edges, because the values between these two are far enough away to not be punished by this function. And so this is very difficult to sample from. Because it's well, the correlation structure is difficult to sample from. So you can't really use, even if you use the covariance of the posterior, it just doesn't really work because you kind of have to move around this space gradually to change it and to visit everywhere in this prior. And so the right is the object we're trying to reconstruct with these priors. Yeah, the forward model is a PDE. This is, the usual thing. This actually describes a electrical impedance tomography problem, but it's the same equations as this subsurface flow that's used a lot as a benchmark in the field. In any case, this the setup was that we have a fine model that's 24 by 24 and a coarse that's 8 by 8. And then we use this adaptive error model that I talked before to correct the coarse model. And they've tried many things to improve the sampler to the right, which basically just takes one pixel at a time and adjusts it and kind of scans over the entire space, but nothing has really improved it except MLDA, because with MLDA you're capable of making a bunch of different changes on the coarse grid before you promote the proposal to the fine grid, which means that you can stay within the prior and perturb the prior and try a little bit here and there until you promote it to the fine, which is something you can't really do with something like a Gaussian proposal. So here the coarse model really kind of was the driver to produce a good proposal for the fine, because you always still with the coarse check correspondence with the prior. So this shows that with MLDA we could really improve this single side metropolis, which had been kind of like the the gold standard for this very difficult problem so far. So that was really encouraging, and we wrapped that up a few weeks ago. Okay, so future directions. I'm always interested in extending like TinyDA. There are some some features from the paper on MLDA that we haven't implemented, including like automatic variance reduction accounting and having different new parameters in the final levels than in the courses, and being able to sample from other proposals there. But yeah, I have a full-time job and don't have all the time in the world to maintain an open source package, but I do what I can when I can. So yeah, you can install it on pip, and there's a GitHub too where you can go and check it out if you like. So yeah, that was all from me. I hope I went a little over time. Sorry.